When thinking about mobile internet, we picture a private pipeline delivering high-speed video straight to our phones. That's what 4G trained us to expect. But our environment is shifting toward an ecosystem of autonomous physical objects, smart city grids, industrial sensors, and self-driving vehicles. 4G architecture was designed to handle human-to-server connections. It lacks the internal logic required for massive, constant coordination between millions of machines at once. If you tried to route the massive data demands of tomorrow's smart infrastructure through yesterday's 4G networks, the system would collapse under the traffic. To sustain a true Internet of Things, we needed a new structural foundation. That is what the fifth generation of mobile communication, or 5G, provides. The first tier of this new foundation is enhanced mobile broadband. As we can see in this animation comparing download speeds, a standard 4G connection takes its time, while the 5G connection reaches 1 to 10 gigabits per second, filling almost instantly. But extreme speed is useless if 1,000 phones are trying to shout over each other to connect to the same standard cell tower. Congestion is the real enemy of mobile broadband. To solve this, engineers redesigned the physical hardware on the towers using massive MIMO. This image shows what that looks like: multiple inputs and multiple outputs, achieved by packing a dense parallel cluster of white rectangular antenna panels onto a single structure. With all those antennas, the tower no longer needs to broadcast a messy radio wave in a wide circle like a floodlight. Instead, it uses beamforming to act like a series of clean, directed laser pointers, beaming data directly to individual users. By combining massive MIMO and beamforming, the network clears up the airwaves. Every device in a crowded stadium gets its own dedicated, interference-free lane. Zooming out from personal devices, 5G takes on an entirely different challenge with massive machine-type communication. Here, the priority shifts from pure speed to managing millions of low-power sensors at the exact same time. Imagine an entire city where thousands of smart meters, refrigerators, and traffic lights are constantly pinging the network with tiny status updates. The engineering problem is keeping all these micro-messages from colliding and jamming the system. The network organizes this chaos using OFDM, a method for efficient data transmission. Here is how it works. A large block of data splits into dozens of parallel subcarriers. It packs these signals tightly together, allowing multiple devices to transmit simultaneously without their signals overlapping. This organizational logic prevents a dense smart city from buckling under the sheer volume of its own digital traffic. Then we reach the highest stakes: ultra-reliable, low-latency communication. In applications like remote healthcare, total bandwidth matters much less than absolute real-time precision. We can see that need in this robotic surgery system. 5G reduces network reaction times down to just 1 millisecond. For an autonomous test car like the one shown here, with its complex roof-mounted sensor array, that near-instantaneous reflex time allows it to process sudden obstacles safely. To guarantee that speed, engineers use network slicing. As shown in this animation, a secure VIP lane is carved out from the main pipeline, allowing life-saving data to entirely bypass standard consumer traffic. That virtual isolation gives autonomous infrastructure a fail-proof, guaranteed lifeline, ensuring critical commands are never delayed by a nearby movie download. It's easy to think of these networks as an invisible web. In reality, executing these three communication scales requires an immense physical toll. Delivering multi-gigabit speeds requires high-frequency bands called millimeter waves. Watch what happens when these waves encounter a solid structure. They cannot travel far, instantly dissolving upon impact with a standard brick wall. Because these signals drop off quickly, telecommunications companies are moving away from isolated towers in favor of deploying thousands of smaller, denser nodes on nearly every street corner. This requires an incredibly high infrastructure cost. Just look at the manual labor involved here. Technicians must physically climb into cherry pickers and install complex high-altitude equipment to keep these dense networks running. Building a purely wireless future ironically demands a physical hardware deployment that is more expensive and dense than any previous generation. These technical tiers, personal speed, environmental capacity, and critical reliability, effectively turn 5G into the operating system for an automated, AI-driven society. These systems must work in complete synchronization to keep our modern physical infrastructure online and responsive. In our upcoming videos, we will explore the deeper engineering behind these systems, digging into the math of real-world wireless implementations like software-defined radios and MIMO. Until then, remember that the 5G icon on your screen is the gateway to a massive web of hardware designed to keep our physical world in sync.